Okay, in this video I'm going to talk about the first part of chapter 24, and it's reflection at a plane surface. Think of that as your flat bathroom mirror. Um, that's just your basic flat mirror. I try to make my diagrams pretty good, so I found my meter stick. There's my mirror. Okay. With a flat mirror, usually, well, always, one of the sides is the side of the incoming light, and the other side is actually dark. We can think of this as being the light side, and this is the dark side. The dark side of the mirror is the part that's pressed up against the wall in your bathroom. We need to draw an axis perpendicular to this, so let's try that. And I'm going to draw an object. I'm going to put my object 20 centimeters out front here. And I'm going to let that object be about 15 centimeters tall, the way I've drawn. So I put it 20 centimeters out in front here, and I do it about 15 centimeters tall. There's no rule that it has to be a certain size. I just want to show you how the light works. First of all, the most obvious light ray that we could draw would be a light ray that just happens to be parallel to this axis. If it hits parallel, comes in right across the tip of this arrow, and it's perpendicular to the mirror, it will turn right around and bounce back out. But when the person's looking at it over there, it can look as if the ray is coming from back here. All this person just sees the ray was coming in, now it's coming out. Your brain tends to follow the rays back to where they think they come from. So an observer over here might think this ray is coming back here someplace, but that's only one ray. We can't locate an image with just one ray. So let's draw another. Suppose that I have another ray. I'm going to let this ray hit, let's see, I'll do that about 15, so right in the middle. Okay, I made this one hit so that if it bounces here, if it's coming in, it hits right there. Again, we want to come just right across the tip. Here's my incoming ray. Well, I know that the angle of incidence equals the angle of reflection. So if I were to draw my normal, here's the normal, it will reflect in such a way that it would go right down like this. Again, we draw this, An observer over here who sees this ray coming out will tend to trace these outgoing rays back to where they think they originate. Okay. Now both this green ray and this red ray crossed the tip of that arrow. But notice from the observer over here, it looks as if both of those rays are coming from back here. That's how we form an image. Notice our image looks to be the same size as our object. You'll also notice that it's right side up. Now I only did where the tip of the arrow is. I can do the exact same process and think about the base of the arrow. Obviously, if I draw a ray that goes across the base of the arrow, that's parallel to the axis, that'll be actually sitting on top of the axis. It'll come in like this, hit the mirror, and go straight back out. Again, it looks like it's coming from back here someplace. If I have a ray coming in at a different angle, not parallel, it's easy to do. Do another green one. It's coming right across this tip maybe. In comes this ray, right across the bottom of that arrow. Again, the law of reflection says it will make an equal but opposite angle. And when it does, it goes off like that. But that appears as if it comes from back here. Okay. So I have a red and a green ray right here at the base. You can see they appear to be coming from right here. Similarly, when I drew this green ray in, it reflected. If I follow it back, it appears it's coming from right here. Okay. That's how a plane mirror works to make an image. Those are probably the mirrors you are most familiar with. This distance from the mirror to the object is called S, right here. S is the object distance. And this distance from here to here is S prime. S prime is the image distance. Write down a few rules for you. These rules are probably also in the notes. I'll make copies of these notes for you. Before I erase that, I should have mentioned this. A plane mirror forms a virtual image. Okay. Because the rays appear to come from behind the mirror. That dark side. We know there's no actual light rays. If I have a mirror and I see an image back here, there's nothing really back here. That's actually probably glued to the wall in my bathroom, okay? It just looks like light's coming from back here. It's because that light's bouncing off this mirror, but your brain traces those rays back and forms an image on the dark side. That's a virtual image. Another thing that's good to know about virtual images is virtual images are always going to appear to be upright, right side up. So when an image is right side up, you know there's not any actual light rays there. It is a virtual image. Let me write some of these rules for drawing images. So to locate an image, and I've already done an example of this for you. First step, draw one ray from the tip of the object we almost always draw our objects exclusively as arrows because that not only helps us see how tall the object is, but we're also interested in whether the image that it forms is going to be upright in the same direction or whether it's going to get flipped back down into the other direction. So arrows are good for that. But the tip of the object, perpendicular to the mirror. So parallel to the axis or perpendicular to the mirror. It reflects straight back. Second step, draw one ray from the tip at an angle. Okay. At an angle to the mirror. Okay. Then all you have to do, you see how it comes back, is follow the law of reflection. The angle of incidence will equal the angle of reflection. Okay. Then you have to do the same thing for the base. Repeat steps 1 and 2 for the base of the object. And finally, you can extend the rays back into the dark side. To find that image. Remember, there's no rays actually behind the mirror. Your eye simply sees two rays coming at it, and it follows those rays back. And when it follows those rays back, the image appears to be from behind the mirror. Okay. We have some sign rules, and sign rules are really important when you start trying to solve problems involving mirrors or lenses, so we might as well try to get these rules straight. I'm going to write down some sign rules for you. Here are the sign rules. For object and image distance. The book has really tried to help us by making rules that we can apply not only to mirrors, but that we'll also be able to apply when we talk about lenses. object distance and the symbol we use for an object distance is that S is positive. When the object is on the same side as the incoming light. Okay. If the object is not on the same side as the incoming light, it will be negative. If we're talking about a mirror, well, with a mirror, the object always has to be on the side of the incoming light, or it's not possible to put the object behind the mirror, okay? When we talk about lenses, we have lots more flexibility on where things can be in front of or behind lenses. So this rule will apply to lenses also, but when we're talking about mirrors, the object distance is going to be on the side of the incoming light, and it's going to be positive. Image distance which is S prime is positive. When the when the image, talking about image now, is on the same side as the outgoing light. Otherwise, negative. Again, images with mirrors and lenses can be both in front of the mirror and the lens, and they can be behind the mirror and the lens. So we need to really pay attention. Image distance is positive only if it's on the same side as the outgoing light. So let's look at what happened. You can pause this if you need to write it. I'm going to move on. What happened with our flat mirror? We have a plain mirror. Here's our mirror. Again, the object was over here. This is the side of the incoming light. Light was coming in on this side. This side's completely dark. Okay. So we had rays that were hitting the mirror. I don't need to draw all of them, but hitting the mirror and then turning around and bouncing off. And some of the rays were coming in at angles and bouncing off at other directions. Okay. Notice the incoming light is over here, but so is the outgoing light. If we're talking about a mirror, this is a mirror right here. The incoming and the outgoing light are both on the same side. They're on the light side. Over here on the dark side, we don't have any light. However, this is where our image formed. Now, an example that I just drew, this distance S was about 20 centimeters. And this distance S prime would be negative 20 centimeters. because it's not on the side of outgoing light. For plane mirrors, S is exactly equal to negative S prime. That means if you're standing 3 feet in front of a mirror, your image appears to be 3 feet behind the mirror. Okay? The object distance and the image distance are the same in magnitude, but the object distance in front of a plane mirror is positive, the image distance is negative. There is a formula also for lateral magnification. Lateral magnification, which is a capital M, is equal to y prime over y, which is the image height over the object height. If we're talking about a plane mirror, these two are the same. So for a plane mirror, better box in that formula, it's a good formula. The magnification is always equal to 1. Okay. So if you have an object, an image formed in a flat mirror, it's going to appear to be the same height as it did as the original object, and it's going to appear to be the same distance behind it. When M is positive, it means that the image is going to be upright. It also means it's going to be a virtual image. Write down a few more things. So, when M is greater than 0, when M is positive, the image is erect. And that also means that it's going to be a virtual image. If the magnification is less than 0, the image is inverted. It's upside down. And that is going to be a real image. If you have a plane mirror, we know the magnification is going to be 1, and it will make a virtual, erect, reversed image. And by reversed image, when you look at yourself in a mirror and you notice that well, if you're married anyway, that your wedding band is on your left hand, it looks as if the person in the mirror is wearing a wedding band on their right hand. So the left to right part is reversed, but it is a virtual image that still appears to be upright. Okay, that's our first lesson, and I'm going to stop right here.